let's work out an example of partial fraction decomposition. Let's look at the following integral. 6x to the fourth power minus x cubed plus 3x squared minus 3x plus 2, everything divided by x cubed, x squared plus 1 dx. So this example looks long, but the key in here is to identify that we have the bottom part, the denominator, to be factored. And that's what is going to guide our work. So in order to use partial fraction decomposition, what we want to do is to rewrite the thing inside of the integral as a sum of partial fractions. So in other words, if we forget for a second about the integral, and if we focus about the rational function that we have over here, that is the main thing that we need to worry about. So having the factored version of the denominator will give me what are the partial fractions that we need to focus on. Notice that the x cubed is actually a repeated factor. In other words, this means that we have the factor x repeated 3 times. This is the same thing as having x times x times x. And then the factor x squared plus 1, notice that that cannot be factored even more. So that is as simple as we can get. And that one we only have it once. In other words, we have a total of 4 factors. This will give me a over x plus b over x plus c over x. We have the x factor repeated 3 times. Since we have it repeated, I cannot have the same expression for all 3 of these. So I need to accommodate for the different powers. In other words, I should have x, x squared, and x cubed. I want to have all the powers up to the top power that we have in here. Then for the last factor, this one corresponds to x squared plus 1. And notice that this is a quadratic factor. That means that the most that I can have on top is a linear factor. So I should include dx plus e. I should not only include one number, I actually have to include both of them, because this whole thing needs to be a proper fraction. And in order to have this to be a proper fraction, the bottom degree is 2. So that means that the top degree has to be 1. That's why we have dx plus e. So this will be the blueprint of the decomposition that I need to use. In other words, what I need to figure out now are the values for a, b, c, d, and e. What we're going to do is we're going to work out this expression and to build a system of equations with this. So the next step for now would be to actually work out the expression to find the system of equations. So for this expression, I will add the fractions that we have over here. And I already know what is the lowest common denominator over there. The common multiple for this denominators will be the exact same expression I started with, which is the x cubed plus x squared plus 1, this part right here. So in order to find the sum of fractions, what I need to do is I just need to work out this fraction. So this will give me this divided by this multiplied by this. I have to get the common denominator divided by one factor multiplied by the top. And that's the procedure that I'm going to repeat for every single term. In other words, the first part in here would be a times ax squared times x squared plus 1. I grab the common denominator, I divide it by the first fraction, and multiply by the first number. Now I repeat the same thing with the second one. In other words, I'm going to have this divided by this one, and then multiplied by this part right here. So that will give me x cubed times x squared divided by x squared multiplied by b. That gives me b times x squared plus 1. Same thing for the third fraction. I grab the common multiple in here, divided by this number, multiplied by this. So that will give me a total of c times x squared plus 1. And then finally, the last part would be to grab the lowest common multiple, divided by the denominator and multiply by the top. So that part will give me dx plus e multiplied by x cubed. So that is the addition of fractions so far. Now what I'm going to do is I'm just going to expand this expression and I'm going to collect similar terms. My strategy in here is to end up with an expression that I can use in order to compare the coefficients of the original expression. So I'm just going to go ahead and add this expression right here. So first of all, I'm going to look for the coefficient of x cubed. If I look at the coefficient of x to the fourth power is the first coefficient that I will get. If I look at the coefficient 2x to the fourth power, I can look at that in every single term. For example, in this term right here, the x to the fourth power would happen if I multiply a by x squared by x squared. That will give me a to the fourth power. So that's the first one right there. And that's the only x to the fourth power coming from that term. Then if I look at this term right here, I cannot make an x to the fourth power. The highest power that I can make is a cube coming from this one and this one. So I don't get anything coming from this part right here. Likewise, from this term, I don't get any fourth power. I can just get a square, so I don't write anything over here. But from the last one, from the last term, I would get a fourth power if I multiply these two. So that coefficient will be a d. In other words, I have that the overall coefficient of the fourth power should be a plus d. Now I move on to the next one, which is the coefficient of the cube. So we look at the coefficient of x cubed. And we see that in the first term, I don't have any cubes. So if I look at this term right here, there are no cubes coming from that. But if I look at this term, I actually have a cube coming from the b, the x, and the x squared. That would give me a cube. In other words, that will give me a b for this part. For the next term, I cannot make a cube. I can only make a square or a constant, so I don't get anything from that. And from the last term, I actually get a cube by multiplying x cubed in here with e. So that will give me plus e. That would be the overall coefficient of x cubed. So notice that what I'm doing is a smart multiplication. So I can actually find what are the coefficients of each of the powers of x. So now I want to find the coefficient of x squared. So a coefficient of x squared, you can see that it's coming from the first term. If I multiply a, x squared times 1, so that will give me a right here. And that's the only x squared that is coming from the first term. The second term doesn't give me an x squared because I have bx, x squared, and 1. So all of them are not going to give me an x squared. However, in the third term, I can get an x squared. If I multiply c times x squared, this is going to give me a squared term. So this will be plus c. And then the last term does not give me any squares. So I don't have anything coming from that one. That means that those are all the squares that I end up with. I'm almost done. I'm looking for x terms. So notice that the first part, this one doesn't have any squares. This one doesn't have any squares. But the second one is a similar way. It doesn't have any x's. Any x's. For this one, I do have an x coming from b and from the 1. In other words, if I multiply b, x, and 1, that gives me a single x. That becomes part of my coefficient. For the next term, right here, this one does not give me a single x. It only gives me a square and a number, so that doesn't work. And this one doesn't work either because then the lowest that I can make is actually the cube. So this one doesn't have any single x's. That means that that's it. That's the only thing I have. Finally, I want to look for constant coefficients. And notice that the first term doesn't give me any constant coefficient because I'm multiplying by x squared. The second term doesn't give me any constant coefficient because I multiply by x. The third term does give me a constant coefficient because I can multiply c times 1. So I have a constant coefficient coming from that one, c, and that's actually the only constant coefficient that I can make. The last term, everything is multiplied by x to the third, so I don't get any constant from that. So all I did was a way in order to smart multiply the numerator for this. I didn't have to expand the whole thing and then simplify. I actually collected powers one by one. So then I would make my life easier because now I know that I can compare the coefficient of x to the fourth power with the coefficient of x to the fourth power. That should be the same. Same thing happens with the coefficient of x cubed, should be the same as the coefficient of x cubed in here. The coefficient of x squared down here is the same as the coefficient of x squared over there. The coefficient of x is the same as the coefficient of x over here. And finally, the constant coefficient is the same as the constant coefficient. So I can actually write down the system of equations that works for me. That means if I look at the first coefficient, that means a plus d equals 6. That's the first equation that I have. The second equation, by looking at the cubes, I look at b plus e. That's the second equation. That will give me a -1 because the coefficient of x cubed up here is actually this negative sign over there, which is -1. If I look at x squared, the coefficient of x squared is a plus c, which will be equal to 3, because that's the coefficient of x cubed up here. That's the coefficient we were looking over there. If we look at the coefficient of x, so the next one is the coefficient of x is just b. So that will give me b equals to -3. That's the value that I have up here. And then finally, the constant coefficient down here is a c. So I have that c equals the constant coefficient, which is a 2. So I have my system of equations over there. Just notice that I wrote it in a funny way, just basically to keep track of all the variables, to be a little bit organized with all the different variables. So I wrote all the a's on one column, all the b's almost in one column, all the c's in one column, and so on. So this is the system of equations that I have. And with these two initial values, I can pretty much solve for everything. So I have that b equals -3. That's from one of the equations. I also have c equals 2. That's another equation. From those values, I can find, for example, the value of a over here. Because I have the value of c, that gives me that a equals 3 minus c. That should be a 1. A equals to 1. Then with the second equation and using the value of b equals -3, I can find the value of e. So e should be -1 minus 3. That should give me -1 minus -3. And that will give me a value of +2. So finally, I can find the value of d because I have the value of a already. And from the first equation, I have d equals 6 minus a, which will be 6 minus 1, and d will be equal to 5. So that was the next step. Once I had the system of equations, I can write down the coefficients for my substitution, basically. So that means that I can go back to the original expression. Let me copy down what I had. So I have 6 x to the fourth power minus x cubed plus 3x squared minus 3x plus 2 divided by x cubed, x squared plus 1. And now I can actually write down my partial fractions because I have the coefficients that I need. So if we look back into my original partial fraction decomposition, I'm just going to plug this coefficients into that partial fraction decomposition. So that means that this will be 1 over x. This is equal to 1 over x. Then the next one is b over x squared, which will be negative 3 over x squared. So minus 3 over x squared. Then the next one is c over x cubed, which will give me 2 over x cubed. So plus 2 over x cubed, plus the final one is dx plus e over x squared plus 1, which will give me 5x plus 2 divided by x squared plus 1. So this is my partial fractions. So this means that I can go back into the original integral. If I want to integrate this whole thing, instead of integrating this big rational function, what I can do is I can integrate the partial fractions. And integrating the partial fractions is a little bit better than dealing with this whole thing. So that means that I just have to do the integral of 1 over x dx minus 3 times the integral of 1 over x squared dx plus 2 times the integral of 1 over x cubed dx plus the integral of 5x plus 2 divided by x squared plus 1 dx. So this expression is much better. All the three integrals, the first three integrals are workable. And the last one, we can basically do a trick. We can separate it and split it into two pieces. In other words, we end up with the integral of 1 over x dx minus 3 times the integral of 1 over x squared dx plus 2 times the integral of 1 over x squared, x cubed dx plus 5 times the integral of 5 over x squared plus 1 dx. So I separated the first one, plus 2 times the integral of 1 over x squared plus 1 dx. Just separated the last integral into two. Now the first three are a logarithm, a power rule, and a power rule respectively. The second one, the integral that we have over here, that is going to be a u substitution. And then the very last one, that we can recognize as the derivative of arctangent. So that means that that integral will end up being the arctangent of something. So this gives me the first one to be natural log of x. That's the first one. The second one would give me plus 3 times 1 over x. So that is a power rule. Notice that the sign changes because the power is negative. The next one should be minus 1 over x squared. So actually this should be a 2 over 2 because of power rule. And the next one, this is a u substitution. So this becomes 5 over 2. And then we have the natural log of x squared plus 1. And then the last one is an arctangent. So this becomes 2 times the arctangent of x, everything plus c. So again, notice that in that second to last integral right here, we just said the u substitution, u equals x squared plus 1, which makes du equals 2 times x dx. And then that is almost what we have over here. So that's why in the end we divided by 2. That's the reason of why we had these two right here. And then that will end up with the integral of 1 over u du, 1/2 that integral. And that will give me the logarithm that appears down here. So that was just a u substitution. So in the end, what we did was we worked out the original expression that we had right here. And the first step is to actually set up this integration using partial fractions, which means we want to decompose that expression using these partial fractions. The partial fractions came from the factorization of the denominator of the original expression. And in this case, we have 3 linear factors and a quadratic factor, which means I want each of these fractions to be proper fractions. The only way that I can make the first three to be proper is if I include only numbers. The only way that I can make the last one to be a complete proper fraction is if the top one is a degree 1. That's why I had to include the dx plus e. In this case, that's all I needed. Then we set up the system of equations and we solved it. And after that, finding the integral was a little bit more straightforward. We just had to do a small u substitution at the very end.